Welcome, 8th graders, to the Dallas Independent School District's STEM Environmental Education Center. We know you can't be here in person this afternoon, but we will do our best to try and make you feel like you're here during today's virtual field trip. If you are watching this and have not registered for this virtual field trip, you can still do that by going to www.tiny.cc/EEC-register to get yourself or your class registered for this field trip. We just use that information for our attendance purposes. Today's field trip is going to be about atoms, and during this virtual field trip, students will discover that matter is composed of atoms and has chemical and physical properties. So we're going to look at atomic theory and the history or early models of atoms, the structure of atoms, valence electrons, and element reactivity. And while we're doing all of that, you can ask us questions, but since this is a virtual field trip, you're going to need to ask us questions through a website. And that website is www.tiny.cc/EEC-question-answer. And you're going to fill out a very short form to ask us any question you like, and as many questions as you like, and we will do our best to answer all of them during our time with you this afternoon. So let's get started with the trip. I'll stop sharing my screen here and turn it over to Mr. Monroe, who is going to share some information about the history of atomic theory.
Hey, good afternoon, 8th graders. My name is Mr. Monroe, and I'm going to be sharing a little information about the history of the atom, especially the atomic theory, and some of the chemists, early chemists and physicists that have finally come to a conclusion about basically a summary of what the theory about the atom is concerning. And this started a long time ago. In fact, one of the earliest guys to publish information about the atomic theory was a fellow by the name of John Dalton. And they want to give him credit for actually starting the atomic theory development. And that was in the early 1800s, but it goes back a lot further than that. Basically, somewhere back around 400 BC, there was a Greek philosopher by the name of Democritus. And he is the first one that actually used the term atom. In fact, the word was atomus, which is a Greek word meaning indivisible. Well, Democritus thought that if you take one piece of matter and you divide it into smaller pieces, you could keep dividing it until you get to one point to where it couldn't be divided anymore. This fundamental or basic unit was what Democritus called the atom. All matter consists of atoms, which are bits and pieces of matter too small to be seen. He believed that. There is only empty space between atoms. Atoms are completely solid. Atoms have no internal structure, and each atom of a different substance is different in size and weight and shape. Those were his thoughts. And then came along the early publisher of the atomic theory, a chemist by the name of John Dalton. His belief was very similar to Democritus. In fact, his model is actually called the billiard ball model. And as you can see, this is similar to a billiard ball. And of course, it was so tiny that you could not see it, okay? In the 1890s, a physicist by the name of J.J. Thomson created an instrument called a cathode ray tube. And he used this tube in an experiment, and through using this as an experiment, he discovered the particles that we call electrons. And he was able to figure out that the electrons were negatively charged. Now, his model, using what he discovered, Thomson predicted that an atom should look like a plum pudding pie. Because of this design that he had designed, that's the name they gave it, the plum pudding model. Each atom is a sphere filled with positively charged fluid. This resembles the sticky jam or part of the pudding. Corpuscles, which were later on called electrons, are negatively charged particles suspended in this fluid. This resembles the plums in the pudding. He did not predict any movement of these electrons. In the 1910s, another physicist came along. His name was Ernest Rutherford. He was convinced about the model of the atoms by Thomson. He thus set up his own famous gold foil experiment. He fired some apple particles that were positively charged at a gold foil. He measured the deflection as the particles came out on the other side. Most of the particles were deflected. Most of the particles were not deflected. Every now and then, a particle would deflect all the way back. He said that there must be a positive center of the foil. So he called the center of the atom the nucleus. Rutherford's atomic model thus then was called the planetary model because he believed the nucleus of the atom is a dense mass of positively charged particles. These electrons, the electrons orbit the nucleus. A problem raised was why are the negatively charged particles not attracted to the positive charged nucleus? Rutherford stated that an atom was like a mini solar system and that the electrons orbited the nucleus in a wide orbit. That is why it is known as the planetary model. During the same time period, another scientist came along. He was a physicist, Niels Bohr. He agreed with the planetary model of the atom, but he also knew that it had some flaws. Using his knowledge of energy and quantum physics, he was able to perfect Rutherford's model. He was able to answer why the electrons did not collect to the nucleus. In his model, the electrons orbit the nucleus in orbits that have a set size and energy. The lower the energy of the electron, the lower the orbit. This means that as the electrons fill up the orbitals, they will fill the lower energy levels first. If the energy level is filled or at capacity, a new level then will begin. And because of the lower energy levels for those electrons being close to the nucleus, they weren't pulled out of that orbit. Now, from Bohr's model, which again, he agreed with Rutherford's model, so that model actually was called the Rutherford-Bohr model. In the 1920s, a scientist, a physicist, this guy was kind of a revolutionary. His name was Erwin Schrödinger. His model was called the cloud model. He believed that an electron does not travel in exact orbit. We can predict where it will probably be. We cannot say for certain where it is, but only where it ought to be. The type of probability orbit is dependent on the energy level that was described by Niels Bohr. Now, these guys, each time they came along, something new was discovered. And every time that was discovered, the atomic theory had to be revised. Today, there's a summary of the atom. And that summary goes like this. The smallest part of an element is called an atom. Each atom of an element is different from the structure of other atoms or other elements. An atom can be divided into smaller subatomic particles, protons, electrons, and neutrons. The nucleus is in the center of the atom. It contains protons and neutrons. Electrons orbit the nucleus. As we go up the periodic table, an electron and a proton is added. Electrons occupy a certain energy level of a certain size. Once the energy level is full, a new level begins. Within each of these levels are special types of orbitals. These depend on the energy level. Each orbital can contain 2 electrons. So there you have it. Students, hopefully I've been able to give you a little information about atomic theory and some of the men who have contributed to that theory and brought us to the point where we are today. Several of those guys they earned a Nobel Peace Prize for their work. J.J. Thomson got a Nobel Peace Prize in 1906. Niels Bohr got a Nobel Peace Prize for his work in 1922. And Erwin Schrödinger got a Nobel Prize for his work in 1933. So you see, all along, we've come to this point now where they basically have had to develop it all along the way to the point where we are today. Thank you for your time. Hopefully you have got a little information from me. And if you have any questions, I'm going to turn it back over to Mr. Broughton so he can answer those for you. Okay, take it away, Mr. Broughton.
All right, thank you, Mr. Monroe. And we do get one question, which is there a microscope that is powerful enough to see just one single atom? And no, there isn't. It's not so much that we don't have powerful microscopes, it's that the atom is so small that it's smaller than a wavelength of visible light. And how we see something is that light has to hit an object, bounce off of that object, and then travel to our eyes. And if a wavelength can't bounce off an atom, then we won't be able to see the atom. And that is why there's no microscope that will let you see one single atom. All right, now let's take a look at the structure of an atom with Ms. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to learn about the structure of an atom. So to review, an atom is just the smallest part of an element that retains all chemical properties of that element. And again, all matter, including us, is made out of atoms. Now, atoms are very small, so the average diameter of an atom is about 0.2 nanometers. So given that, if I were to show you guys a penny, how many zinc and copper atoms do you think make up this single penny? So the answer is it's a really big number. So it's called 2 sextillion atoms make up a penny. And if you were to write it down, this is what that number would look like with all these zeros. So instead of writing that large number down, scientists use what's called scientific notation. And that's a shorthand way of writing large numbers. So in this case, the scientific notation way of writing 2 sextillion is by writing 2 times 10 to the 22nd power. So again, atoms, very, very tiny. So if this is how many atoms make up a penny, imagine how many atoms make up a human being. That's a lot. So now we're going to look at the structure of an atom. I'm going to show you guys this model. So if you look at this model, what are some things that you notice? Can you identify any of the parts that you see here? So let's start with the nucleus. Inside the nucleus, we have protons and neutrons. So we're going to start off with protons first. Protons are positively charged particles, and the way I remember that is proton starts with a P, positive starts with a P, so I just call them positively charged protons. So in this model, my protons are going to be the red dots. Now protons, if an atom is small, just imagine how small a proton is. So protons are very small and they have very little mass. The mass of one proton is negative 1.7 times 10 to the negative 24 grams. And if you were to write that down, this is what that number would look like. So again, super tiny mass. The mass of a proton is so small that scientists had to create a new unit to describe their mass. So they call this new unit a unified atomic mass unit. So the mass of one proton is simply 1U. And again, protons are your positively charged particles. The number of protons that are inside each element will always be the same. So just remember that. That will come in handy later on. The next thing that we notice that's inside our nucleus are these blue dots. What do y'all think those blue dots represent? The blue dots are going to be neutrally charged particles called neutrons. And that one's also easy to remember because they both start with the letter N. So neutrons are neutral. They have no charge and they have very little mass, just like a proton. And the number of neutrons that are within each element of an atom can actually change. And when that happens, we have what's called an isotope. So an isotope is just an element. It's the same element, but it has different number of neutrons. So one of the elements, isotopes that we're going to look at today is carbon-14. and we'll talk about that one in just a second. So just know that the number of neutrons that are inside an atom for a particular element can actually change, and when that happens, we have what's called an isotope. What else do you guys see in our model? Well, I see these yellow dots. Those yellow dots are electrons, and electrons are even smaller than the protons and neutrons. They have a negative charge. They exist outside the nucleus. And as Mr. Monroe explained, Bohr thought in his model that they went around the nucleus in sort of like an orbit similar to the planets. However, we now know that the electrons kind of scatter in what's called an electron cloud. It's impossible right now to determine the exact location of electrons just because they're moving so fast and they're so tiny, but we do know that they're somewhere in an electron cloud region. Typically, the number of electrons is equal to the number of protons. However, that can change. So the number of electrons for a particular element can change. So electrons can be lost and they can be gained. And when that happens, we have what's called an ion. And we'll talk more about that in just a second when we do our simulation. So now that we know we have positive protons, neutrons, and negative electrons, we're going to see how did we find that information. So if you want to figure out what atomic structure does this model represent, you can look at a periodic table. And the periodic table will help you identify it. So we know that this model has 6 protons. So we're going to look at the periodic table and we're going to look for an element that has an atomic mass of 6. In this case, I know that that would be carbon. So this is a model of a carbon atom. Also, if you're looking at a model, what are some limitations of this model? It's not a perfect model, so obviously we know that the sizes are off. An atom is not that big. We also know that the sizes of the protons, neutrons, and electrons are not proportional on this model as well. We also talked about the differences between the Bohr model and the electron cloud. So those are some limitations that are in this model. So now that we know how to find the atomic structure using a periodic table, let's look more in depth about the cell within the periodic table. So here's our periodic table right here. Now, if you were to show you a close-up, since we looked at a carbon model, we're going to look at the carbon cell of the periodic table. We have a big C that represents the chemical symbol. The atomic number we talked about earlier is the big number on top. The atomic number tells you the number of protons, and the atomic number element will never change. The atomic number tells us the number of protons, and usually the number of protons is the same as the number of electrons. However, that can change. If that does change, then you have what's called an ion. On the bottom, you have the chemical name or the element name. In this case, we know it's carbon. And then on the very bottom, you have the atomic mass. The atomic mass is just the mass of the number of protons plus the number of neutrons, and that gives you your atomic mass. Now, we talked about isotopes earlier. So this is a typical carbon atom. Now let's talk about an isotope. A common isotope is carbon-14, written as C14. It can also be represented in this diagram here where we have a big C, the atomic mass on the top, and the atomic number on the bottom. Now notice this is the isotope of carbon. The atomic number did not change, so that will stay the same. However, the mass changed. In a typical atom of carbon, the mass is 12. However, in this isotope, the mass is 14. Now, if you want to find out how many neutrons are inside carbon-14, all you have to do is do a simple math problem. And I'll show you an example of what that looks like. So we know atomic mass is simply number of protons plus number of neutrons. In our example, we're using carbon-14. 14 is telling us the atomic mass. So carbon-14 has an atomic mass of 14. So we set up a simple equation to find the number of neutrons. We know that protons plus neutrons equals the atomic mass. We know by looking on the periodic table that carbon has an atomic number of 6. So it has 6 protons. We're trying to find out how many neutrons are in carbon-14. So we're going to denote that by N. And we know carbon-14 has a mass of 14. So to solve the equation, we're just going to take away 6 from each side to balance it. And that tells us that carbon-14 has 8 neutrons. So you can find pretty much all the information you need using a periodic table. The next thing I want to do is show you and build your atom simulation. So I'm going to share my screen. And hopefully you can see it in just a second. So we're going to look at this simulation. This is pretty cool because you can play around and experiment with building different atoms. So for example, I'm going to drag one proton to this model. If I put one proton into this model, what element will I be representing? And again, you can look at a periodic table, and we know that the element that has one proton is going to be hydrogen. Now we're going to see what happens if, now we know that hydrogen has one proton, so it should have one electron, so we're going to add that. We have a neutral atom because we have one positively charged particle and one negatively charged particle. Now let's see what's going to happen if I add another electron. Notice it now says an ion. So again, if you change the number of electrons for an atom, it becomes an ion. In this case, it's a negative ion because I now have more negative charged electrons than I do my protons. Now let's see what happens if I add some neutrons. So there's one neutron. Now let's see what happens if I add two neutrons. So by changing the number of neutrons, I now create an isotope. So isotopes have different number of neutrons. Now this isotope happens to be unstable. So you can play around with this. It's from it's fet.colorado.edu, and it's the atom builder. So you can explore and play around with changing the number of protons, neutrons, and electrons to see how that affects the atom stability, whether it's going to be a neutral or an ion. So that one's something pretty cool to look at. We're going to come back, and I'm going to stop presenting. There we go. And now we're just going to do a super quick review. So to review, we talked about atomic structure. This one happens to be the atomic structure for an oxygen atom. And again, I just used the periodic table to help me draw this diagram. The middle, we have the nucleus. The nucleus consists of protons and neutrons. Protons are positive, neutrons are neutral, and the nucleus contains most of the mass of an atom. Then around the nucleus, we have our electrons. Electrons are negatively charged, and we know that they kind of float around and move within an electron cloud. Then we talked about isotopes. And isotopes are atoms of the same element, but they have different numbers of neutrons. So we talked about carbon-14. That's a super important isotope because scientists use it for carbon-14 dating. So they use it to determine how old organisms and plants are. Very important for the fossil record. Now we do use other isotopes. One of the more important isotopes that we use is cobalt-60, and that is used for chemotherapy for cancer patients. So it's important to learn about isotopes and atoms because we can use them for our advantage. So cobalt-60, let me show you what a regular cobalt atom looks like. And this is just an app you can put on your phone or your iPad. It's for the periodic table. And this one happens to be what the typical cobalt atom looks like here. Now, my challenge for you guys is to see if you can figure out how many neutrons are in the isotope cobalt-60. So think of your math equation and how you can use the periodic table to help you find the answer to this question. And then I have just a really simple reflection question. I just want you to think about why is it important to learn about atoms and how does this relate to us? And that's all I have for you guys today about atomic structure and isotopes. We're going to give it back to Mr. Broughton, and he's going to answer any questions that y'all might have.
All right, thank you, Mr. Mears. And the question came in was, for an atom of carbon, can an isotope have any number of neutrons? Because we saw that it could have 12 or 13 or 14, but it cannot have any number. If you take away too many or add too many, it becomes unstable and cannot exist in nature. So we've learned a little bit about electrons, but now we're going to talk about valence electrons, which are special electrons and that Mrs. Fuller is going to teach us about.
Good afternoon. We're going to talk about valence electrons, which are the electrons in the outer shell of the atom, and they're the ones that determine the atom's properties, chemical properties. So if you look at the periodic table, if you look at the groups as they go across, it's going to tell you, it's very easy to figure out how many valence electrons are in the outer shell of each of these atoms. So in group 1, it's got one atom, one valence electron in its atom. Group 2, 2 valence electrons. Group 13, 3. Group 14, 4. Group 15, 5. Group 16, 6. Group 17, 7, and group 18 has 8. Now there's a law or a rule called the octet rule, which is the atoms want their outer shell, their valence electron shell, to be complete with 8, hence the word octet, with 8 valence electrons. So these elements right here, those are the noble gases, and they don't interact with other elements because their outer shell is complete. It has 8 valence electrons. So we're going to look at a couple of molecules and talk about how they bond with the valence electrons in order to fulfill that octet rule, that rule of 8. So let's start with sodium chloride. Now, sodium chloride is nothing more than salt, just plain old salt. In nature, it occurs as halite, this little cubic crystal. And the sodium, when you look at it on the periodic table, right here, it has 11 electrons, but it's in the first group, so only one is a valence electron. So this one, this sodium chloride, this is chlorine right here. Chlorine has 7. It's in this column, the 17 column. So it's got 7 valence electrons. So what does chlorine want? It wants one more to fulfill the octet rule. So what happens here, it's pretty interesting. The sodium is a metal. The chlorine is a non-metal. So metals give up their electrons to non-metals. So we give up that 11th electron, that valence electron, that one valence electron that sodium has, and gives it to chlorine. And so chlorine now has 8, and sodium is left with its 2 inner shells, the first shell having 2 and then the one after that having 8. So they're loosely bound together. Now, remember what Ms. Ramirez told you about ions, and this sodium gave up an electron, and gave it to the chlorine. So this is an ionic bond because this is now an ion. So they are loosely bound primarily by charge, and they don't occur like this in nature. They form a lattice, a crystalline lattice to form the crystal, this cubic crystal, halite or salt. This is a framework of atoms that are bonded together in an ordered manner. It always is going to look like a cube. It's very symmetrical. The most basic part is called the unit cell, and this is the smallest repeatable unit of the atoms. So they're aligned with the salt cleavage. If you break this thing, it's going to break into a cube every time. It's got cubic cleavage. So that's sodium chloride for you. Now this is a different type. This is a water molecule. And when you look on the periodic table, hydrogen is in column 1. So it's got 1 valence electron. Oxygen is in group 16, so it has 6 valence electrons. So these 2 atoms of hydrogen are not going to surrender their valence electron to the oxygen. They're going to share it. So it's a different kind of bond than what you saw with sodium chloride. So in order for the octet rule to be fulfilled, for the oxygen to have its 8, it's going to share a valence electron with each of these 2 hydrogen. But you think about the nucleus of the oxygen, it's got 8 protons. So it's the activity of the electrons are going to spend most of their time on the oxygen side of the molecule. So what does that do to the molecule? It gives it polarity. This top part is going to be slightly positively charged. The bottom part is going to be slightly negatively charged. It's the polarity of the water molecule that enables it to be the universal solvent. When you're in the 4th grade, you learned that water is the universal solvent. It'll dissolve more things than anything else. And the reason why is because of the polarity of the water molecule. This water molecule also exhibits a characteristic called cohesion. The water molecules are attracted to one another. So because of its polarity, have you ever been in a rainstorm and seen the water droplets on the windshield and how it forms a little dome? That's because of the cohesive nature of this polar molecule. So water is very fascinating. It's very important to us as living organisms. And I hope you learned a little bit about valence electrons. Thank you so much. Good day. Mr. Broughton will answer any questions that you might have.
Thank you, Mrs. Nash. And the question that came in is, when sodium reacts with chlorine to form salt, and it gives that valence electron to chlorine, does it have any more electrons left? And let's take a look at this periodic table to help us answer that. Oh, but I better share my screen first so you can see what I see. So here we go. Screen sharing is on, and here is a periodic table of elements. We have sodium right here, and this 11 is the atomic number, so that is the number of protons and electrons in an atom of sodium. And over on the other side, we have chlorine with an atomic number of 17. That means it has 17 protons, 17 electrons, and how those are arranged is that there's 2 protons in the first shell, then 8, and then it would be 7 until it gets 1 from sodium. And then this sodium gives away 1, so it would go down to 10, but it would still have 10 electrons left, 2 in the first shell, 8 in the next shell. So it likes that rule of 8 because it's got 8 in its outermost shell. And chlorine is also happy because it now has 8 electrons in its outermost shell. And so that's part of the reason these are so reactive together and what makes salt so common on Earth. All right, now let's go into more about reactivity with Miss Nash.
Hello, good afternoon. Welcome to my classroom. And today we're talking about reactivity. So reactivity refers to how readily, easily, or quickly a substance will undergo a chemical reaction. And this can happen on its own or with other compounds. It usually also involves the release of energy. So we can see this happening around us. You can see my favorite, rust. So rust occurs with iron, with water, and the air. And it's a chemical reaction. And it will keep on happening. It's slow, pretty slow, but you hear it flaking off. Flaking off, more new iron is revealed, and it will keep on happening. Now, again, chemical reactions are dependent on the properties of the substance. So this happens slowly. It's a metal. But particle size will influence it. So if I take steel wool, in comparison to my railroad stake rather, this has been in my classroom for a long time, and it's slightly rusted, but not too badly. But if I take my steel wool and it's all tiny particles, this will rust overnight. And you can try this at home. You can test different things, like if you put water and compare it to salt water. Which one do you think will make it rust more quickly? You can also amaze your friends and family by making a balloon go inside a bottle. Steel wool, water, a balloon on top, and overnight, that balloon will be pulled down into the bottle. Because that oxygen that was taking up all that space, it was a gas that needs room, now has become iron oxide. And so now it's a solid and it takes up much less space. And as a result, it creates a vacuum and it just pulls that balloon down inside. Now we can, again, like Mr. Fuller said, we could use that periodic table and the valence electrons to predict how reactive something will be. So the most reactive things will be in the bottom left and the top right, except of course for our friends, the noble gases. They're so high and fruity and high and mighty that, like neon, helium, and the rest, they have all the electrons they need. They don't need any more for us commoners here. It's the octet rule. So they are very inert. So I call them noble. They don't go anywhere. They're just there. So, and again, looking at the valence electron, if you have less than 4, you like sodium, you want to lose that one. Okay, it's kind of out there all by itself. You want to lose that. Nitrogen, okay, with 5, wants to gain. Okay, so if you have 4, you can kind of go either way. But more than 4, you want to gain, and less than 4, you want to lose. So you can predict the reactivity of elements depending on where they fall in the chart of the valence electron. Now we're going to do a really quick little demonstration here with a common substance that you may have in your medicine cabinet. I had it in my gardening equipment cabinet. It's hydrogen peroxide, H2O2. And having researched this a bit, I will not be buying it anymore because it involves the production of this, involves a lot of fossil fuel and toxic waste. So this will be my last bottle. But you'll notice it's in a brown bottle. That's to prevent sunlight from entering. It also will have a little hole in the top because it's so reactive that even in a bottle like this, oxygen will be getting out of there. It doesn't want to be there. Okay. And I use it in the garden I mix it with water and then spray it on, if the plants get mildew, it will kill the mildew. And it's very non-toxic to the plant because it decomposes down into water and oxygen. And if I just pour it out and leave it for a while, it will also just decompose, go back to being what it wanted to be in the first place, water and oxygen. It doesn't like to be H2O2. So we're going to have a little demonstration here. Let me pour about 150 milliliters into my flask here. And I'm going to add a little bit of dish soap. Okay. Because we want to be able to see when that oxygen escapes. Okay, so it's trapped in there right now, but it wants to get out. Let me out of here. We'll food coloring just for excitement. And now I have my magic ingredient here. I'll check it up a little bit. I have it's a catalyst. Okay, so this is a catalyzed reaction. So if I left this for a while, it would happen anyway. But this way, you can really see it happen. I'll put on my goggles just for show. So yeast, you might use it to bake, for baking, making bread, right? So those bubbles in there show that something's happening. It's releasing a special chemical enzyme called catalase. Let's see what happens. What do you think? Here comes the oxygen. Just let me out of here. Let me out. Let me out. There. Okay. So the catalyst makes it happen more quickly. Okay. Again, it would happen all by itself, but this way it's going to go really fast. Okay. And it's also a little bit warm because it's an exothermic reaction. So that's all I have for you, and Mr. Broughton will answer any questions.
Thank you, Ms. Nash. The question that we got was, what is the most reactive element? And I'm going to share my screen one more time to try to answer that. There we go. And if we go back to the periodic table of elements, the most reactive elements are over here in this lower left-hand corner. So the far left and lower left-hand corner is francium, but depending on which resource you look at, some will say it's cesium and some will say francium. The reason that everyone doesn't say francium is there is not very much francium on Earth. It's very rare to find, and its half-life of its most common isotope is only 22 minutes. So it's difficult to experiment with francium. Cesium is a little more stable and more plentiful, so they will use that instead. And the reason these ones in the lower left-hand corner, especially these two, are the most reactive is that they've got that one, because this is group 1, valence electron, and it is so far, being that they have atomic numbers of 55 and then all the way up to 87, from the nucleus, that it's easy to get away compared to sodium, which that valence electron does easily go to chlorine, but it's much closer to the nucleus than the electron for these. So that's why these are the most reactive elements. And now I'm going to go over to this, and we'll do a quick recap of what we looked at today. So during this virtual field trip, students discovered that matter is composed of atoms and has chemical and physical properties. Mr. Monroe went over atomic theory and history of early models of atoms. Ms. Ramirez showed you the structure of atoms with the protons, neutrons, and electrons. Mrs. Fuller explored valence electrons. And Ms. Nash showed you that really cool exothermic reaction to illustrate element reactivity. So thank you so much for joining us this afternoon. Please let us know what you think about this field trip by going to www.tiny.cc/EEC feedback and giving us feedback on today's field trip. We use that to improve what we do, and would appreciate your feedback. So now I'm going to stop sharing my screen here and wish you a great rest of your afternoon. Have a good day. Bye-bye.